Good morning, good afternoon, good evening, no matter where you are around the world. Welcome to Kilroy's World. I'm Al Forte. Welcome to my office. See, it's the world back there, right? So tonight we're going to talk about soldering, and we're going to talk about different solders, different soldering iron wattages. Oh yeah, what I was going to say is this module is going to be there's a little kit back at the let me bring it up. So in this folder, I've got a quiz that I'll hand out later on, or actually I'll post in Blackboard. And then we've got this nice little cool kit that's a little robot. So you can call it Kilroy if you want. But basically what it is a kit that teaches a little bit about LED identification, transistor types, a little resistor code. These are the parts the kit has in it. The kit will consist or kind of look something like this. Look, it's even got Kilroy's little squiggly up there. It's a skill level 1 quiz, so it's not a really hard quiz. Let's see if I can get to the second one. Oh, there's the quiz. You saw the quiz. I think I got to go backwards. There's the second page with the instructions, and we'll go over it later on. Okay, but it kind of talks about the different things to do with it, and I will go over it, but I'm just bringing it up so that you'll basically know what the final, project's going to be, or not the final project, but the goal of this chapter or this module. It'll be soldering all those components on there, and it'll be some of the assembly instructions and how the LEDs are wired and such, and we'll discuss that. Is that page 4? That is page 4. Now, there is one other thing, and what I'm going to do is I lost it. What I'm going to do is I'm going to go ahead and run it and watch it. It's an old video back from 1979 that we show. So there's a video. Let's start it out. It's about 35 minutes long, but I'll start and stop it. I'll make some comments about it as we go along. Anyway, here we go. And like I said, it's old. And I don't need to be in the way.
Electronic equipment consists of many circuits combined in such a way as to perform the job we need done.
These circuits are made up of individual components such as resistors, capacitors, diodes, transistors, and integrated circuits, with their leads interconnected together in various ways and bonded by soldering. Just one sloppy solder connection can cause all this equipment to completely fail. That's why it's so important to learn how to solder properly. In part 1 of this 2-part program, we'll cover what is soldering, wetting, solder, flux, soldering irons, and tinning. Soldering is a skill that requires both knowledge and practice. By watching this program and then applying what you've learned, you'll soon be making good solder connections automatically. Soldering is the joining together of metal parts by applying solder and heat to them. When the solder is heated to a high enough temperature, it becomes a liquid, which flows onto and slightly penetrates the metal surfaces of the connection. As it solidifies, the solder bonds the metal surfaces, producing a good electrical and strong mechanical connection. The basic purpose of soldering is to make a good electrical connection. that's also mechanically strong. Each time you make a good connection, the solder is heated to its melting temperature and flows over the leads to be interconnected. The solder actually penetrates into the pores of the metal to be soldered. This embedding of the solder into the surface of the metal leads is called wetting. Good wetting is indicated by the solder feathering out to a thin edge. This is an example of good wetting. Notice the solder feathers out to a thin edge. It's the wetting process that actually provides the physical strength and makes the good electrical connection. Here's another example of good wetting. The ability to wet the leads with solder is the secret of good soldering. The solder used in electronics is a mixture of tin and lead. Both tin and lead melt at temperatures much lower than most other metals. So the applied heat melts the solder but not the leads. That's why solder can be used to join metal leads and wires so conveniently. The tin and lead can be mixed in different proportions to make solders with different characteristics. For example, this is 40-60 solder. It's a mixture of 40% tin and 60% lead. This is 60-40 solder, the most commonly used type of solder in electronics. It's a mixture of 60% tin and 40% lead. Solder is normally solid, but becomes soft or pasty when you apply enough heat. As more heat is applied, it melts and becomes a liquid. The proportions of tin and lead determines the solder's melting temperature. For example, 60-40 solder has a lower melting temperature than 40-60 solder. This means you would not have to heat the connection as much to melt 60-40 solder, thereby reducing the chance of damaging a delicate component or printed circuit board. Another advantage of 60-40 solder is that it has a narrow temperature range where it's soft. Because 60-40 solder quickly changes from a liquid to a solid, there's less chance for lead movement to occur while the solder is soft, causing a poor connection. A low melting temperature and a narrow soft range are two reasons why 60-40 solder is the most commonly used grade of solder for electronic work. 63-37 solder is even a bit better, but more expensive. It has a slightly lower melting temperature and changes from solid to liquid without going through a soft state. So the two best tin-lead ratios for regular soldering are 60-40 and 63-37. To make a good solder connection, the wires and leads must be clean. This looks like a clean connection, but because it's exposed to the air, an invisible insulating oxide layer has formed on the metal surfaces. The solder will not flow and stick to the wires unless the oxide is removed. Removing the invisible oxide layer is the job of a chemical substance called flux. Most solder used in electronics is actually a type of miniature tubing that contains the flux built into it. The flux automatically removes any oxide from the metal to be soldered as you apply the solder to the heated connection. The two most common types of flux are rosin and acid. Acid core solder should never be used for soldering electronic connections because it is highly corrosive. Acid core solder is used primarily in sheet metal work. Only rosin core solder should be used in electronic soldering. Rosin core solder is available in several diameters. The larger diameters are used for most general electronic work, such as terminals and connectors. The smaller diameters permit better control of the amount of solder being fed to small connections, such as those on printed circuit boards. To make a good connection, you've got to heat it to a temperature somewhat above the melting point of solder. That's the job of the soldering iron. Soldering irons come in many sizes and shapes. They're rated in terms of wattage, an electrical characteristic that tells how much power they consume. The amount of heat that a soldering iron will produce depends upon its wattage. The bigger the connection, the more heat it drains from the iron, so the higher wattage iron you'd need. For most electronic work, you should use a pencil iron with a wattage rating in the 25 to 60 watt range. For your own personal safety, you should use a soldering iron with a 3-wire AC power cord. This wire grounds the iron's exposed metal frame and tip to prevent electrical shock hazard to the user. In addition to safety reasons, a grounded tip helps protect voltage and current-sensitive components, such as delicate MOS ICs and MOSFETs. These devices are very sensitive to leakage electricity and static charges. A pulse discharge from a soldering iron can ruin sensitive MOS devices. So always use an iron with a grounded tip. Never solder in circuits that are on. If the iron's grounded tip touches a live circuit, you'll cause a short circuit and possibly damage the equipment. Some irons allow you to change to different temperature tips. This iron features 600, 700, and 800 degree Fahrenheit tips. Changing tips allows you to adapt the iron for different temperature ranges. Select a tip temperature based upon the size of the solder connection and the temperature sensitivity of the components. A 700 degree tip temperature is good for soldering or unsoldering most electronic connections. A 600 degree tip is good for PC boards with thin or delicate foil, while an 800 degree tip is good for connections with more area to heat, such as multi-layer printed circuit boards. Don't confuse heat with temperature. Heat is what brings the connection and solder to its melting temperature. It's important to transfer heat from the iron's tip to the connection as fast as possible so as not to damage the PC board or components. That's why soldering iron tips come in many sizes and shapes. This allows you to select the tip that transmits the most heat and allows greatest accessibility to the surface you plan to solder. As you begin heating a connection, your main concern is to place as much heated soldering tip surface in contact with the connection as you can. Two shapes that allow you to do this in most cases are a pointed tip, such as the conical or pyramid, and a flat-sided tip, such as the screwdriver or chisel. The screwdriver or chisel tip works well when you solder wires to flat terminals. The conical or pyramid tips are good for soldering thin wires and component leads to holes in PC boards. As you use your soldering iron, its tip will become dirty because of a buildup of oxides and dirt. All this contamination reduces the amount of heat that can be transferred from the iron to the connection. That's why you should get into the habit of cleaning your iron's tip practically every time you pick it up. You can do this by quickly wiping the tip across a damp sponge just before you use it. Most tips are copper, plated with iron or nickel. Never clean plated tips by filing them, or you'll greatly reduce the tip's life. Instead, get into the habit of wiping the tip before you solder. After your tip is clean, you should tin it. Tinning means coating the previously cleaned tip with a layer of fresh rosin core solder. A good coat of solder will protect the tip from oxidation and increases the amount of heat transferred to the connection. There should always be a layer of bright solder on your iron's tip. That's why you should get into the habit of regularly cleaning and tinning your iron. Once tinning is complete, you're ready to solder. In summary, we've seen that soldering is the joining together of metal parts by applying solder and heat to them. The basic purpose of soldering in electronics is to provide a good electrical connection that is also mechanically strong. In any properly made connection, the solder actually penetrates into the pores of the metal being soldered. This embedding of the solder into the surface of the metal is called wetting. Good wetting is indicated by the solder feathering out to a thin edge and is the key to making a good solder connection. Don't confuse wetting with tinning. Wetting means the solder is penetrating into the pores of the metal to be soldered. Tinning means a coating or layer of solder on the metal. For example, we can tin a wire or tin the iron's tip. You should clean and tin your iron's tip regularly in order to make good solder connections. Use rosin core solder with a 60-40 or 63-37 tin-lead mixture. These are the two best grades for most electronic work. A pencil iron with a wattage rating in the 25 to 60 watt range works best for most electronic work. Use a soldering iron with a grounded frame and tip for your own personal safety and to help protect sensitive components such as MOSFETs and MOS ICs. Soldering iron tips come in many sizes and shapes. Select a shape that'll give maximum contact between the tip and work, and that also allows for easy accessibility. It's important to remember that the purpose of a soldering iron is not to melt the solder itself, but rather to heat the solder to a high enough temperature to melt the solder when the solder contacts the work. In part 2 of this program, we'll cover how to solder and unsolder. After viewing part 1, you should now have a good understanding of the basic tools and techniques needed to solder. In part 2, we'll cover how to solder and unsolder. To test your retention, there'll be a short quiz at the end of this program. In order to solder properly, you've got to make sure that all surfaces to be soldered are clean. New components are usually clean and in solderable condition, so there's nothing for you to do to them except keep your fingers off the leads as much as possible. Parts that have been in stock for a long time could have a coat of oxide on the leads. One way to clean the leads is by scraping them. Remember, the basic purpose of soldering is to make a good electrical connection that's also mechanically strong. A mechanically strong connection means that instead of just passing a wire or lead through a terminal hole, you should wrap the wire around the terminal. By mechanically securing the lead, you'll get a more solid physical support, and it'll also keep the lead from moving while the solder is cooling. On printed circuit boards, components are usually mounted flat against the board. Now you're ready to solder. The 4 basic steps to soldering are: wipe the tip clean, heat the connection, apply the solder to the opposite side of the connection, leave the tip on only long enough to thoroughly melt the solder. Let's try this. First, clean the iron's tip by wiping it on a damp sponge. Tin the tip if necessary. The tip must have a good coat of solder to quickly transfer heat from the iron to the connection. Then heat the connection by placing as much tip surface as possible against both the lead and foil. Apply the solder. A small amount of solder applied to the tip will help the transfer of heat. Then the solder should be moved quickly to the opposite side of the connection. Remove the solder first, then the iron. Let the connection cool undisturbed. Then cut off the excess leads. It's good practice to remove the flux residue after soldering because it doesn't look good and it tends to collect dust and other foreign matter which could cause electrical leakage paths. After the solder has solidified, the flux residue should be dissolved with an approved solvent. Applied with a bristle brush or sprayed, and the dissolved residues removed with industrial wiping tissues or other absorbent material. A clean part of the tissue should be used each time to avoid the possibility of transferring the dissolved flux back to the connection. Then check your work. Remember the key words, smooth and shiny. A good connection is smooth and shiny. The solder should feather out to a thin edge. This is a good connection. Now let's look at some poor connections. This is a cold solder joint. It has a dull, gray, grainy, or crumbly appearance with poor bonding quality. Cold solder joints are usually caused by lead movement while the connection was cooling or by insufficient heat. This is a good connection. This is an excessive solder joint. It has more solder than is necessary to make a good connection. The heavy solder buildup obscures the wire or lead outline. Excessive solder joints are usually caused by applying too much solder or using too large a diameter solder. An insufficiently soldered joint does not have enough solder to provide a good bond between the wire and the terminal. It can occur if not enough solder is used to cover the connection or using too small a diameter solder. Burned or melted insulation is unacceptable and should be removed. The insulation must be close to the solder connection, but must not be included in the joint. Be careful not to make a solder bridge when working on connectors with closely spaced terminals or on PC boards. Solder bridges occur when adjacent terminals or traces are accidentally soldered or shorted together due to using too much solder. Using too much heat is the #1 cause of PC board soldering faults. If you overheat the green-colored epoxy glass PC boards, you'll cause white spots called measling. In addition to not looking good, measling can introduce paths for leakage and contamination. Measling is unacceptable if there is a continuous path between two conductors or pads. Too much heat can also cause a pad to lift. Make it a habit to apply the least heat possible to do the job properly. If you have to remove and replace a defective part, or if you solder a wire to a wrong terminal, you'll need to know how to unsolder. The tools you use to solder can also be used to unsolder. However, unsoldering can be done much more easily with tools especially designed for the job, such as a vacuum bulb, solder sucker, desoldering iron, or desoldering wick. The best way to unsolder a connection is to remove the solder from it and then disconnect the leads. Here we're using a solder sucker to remove the solder. To use it, you cock it by depressing the plunger. Then melt the solder on the connection, remove the iron's tip, and quickly insert the tip of the solder sucker into the molten solder. Release the plunger, and the solder will be drawn into the sucker. Allow the joint to cool, then repeat this procedure if necessary so that you remove as much solder as possible. Removing as much solder as possible will make it easier for you to free the leads without damage. The vacuum bulb and desoldering iron are used in a manner similar to the solder sucker, except that you release a squeeze bulb instead of a plunger. A key point to always keep in mind when working on PC boards is to avoid excessive heat. That's why you should never put the tip of a solder sucker or vacuum bulb on top of the iron. This extra pressure can cause the iron to burn the board. Desoldering wick or braid can also be used as an easy and effective way of unsoldering a component or touching up a printed circuit board. It's especially useful in unsoldering hard-to-reach connections where a vacuum device won't fit, or where the solder to be removed covers a large area, such as a solder bridge. Desoldering wick is a mesh of fine stranded rosin-coated wire that absorbs solder like a sponge absorbs water. It comes in several widths to allow you to select the one best suited for the connection you want to unsolder. To use desoldering wick, place some of it on the connection to be unsoldered, then press a hot iron against the wick. The solder is drawn up into the wick as the iron melts the solder. Remove the wick and soldering iron simultaneously. After you're done, cut off and discard the part of the wick that is filled with solder. As with any desoldering technique, it should be repeated as necessary to make sure all the solder is removed. After you remove the solder from the connection, it should be fairly easy to remove the lead or wire with long-nosed pliers. Pry the lead loose gently, breaking away whatever thin layer of solder is left holding it. Be careful, as you can still cause damage. Removing ICs from printed circuit boards is probably the most difficult type of unsoldering. If you don't need to save the IC, you can cut each pin. The IC body is then removed, leaving all the pins still soldered in the board. The pins can then be removed one at a time by heating them with a soldering iron and pulling each one out with needle nose pliers. The clip-out method is also a good way to unsolder components with thick leads. Thick leads require more heat to unsolder, which could cause the PC board pad to lift. By first clipping out the component, you'll need less heat to unsolder the connection, so there's less chance of heat damage. Then each hole must be cleared of solder. You can use a vacuum bulb, solder sucker, or insert a toothpick in each hole to force out the old solder. If you need to save the IC, you can unsolder it by heating each lead, then remove the solder using a solder sucker or vacuum bulb. One way to do this is to rest the tip of the solder sucker against the pin next to the one you're unsoldering. When the solder is melted, just roll the tip of the solder sucker over it and release the plunger. Repeat until all IC leads are free. Carefully move each IC lead with long-nosed pliers to be sure that it is mechanically free from the PC board. You may have to repeat with the iron and solder sucker for some leads. After all leads are free, you can remove the IC by gripping the top and bottom with long-nosed pliers or an IC extractor and gently roll it out. Carefully remove all remaining solder from the PC board holes with a toothpick or solder sucker. In summary, we've seen that in order to make a good connection, the metal surfaces must be clean. Ensure a good job by getting off to a clean start. Mechanically secure the wire or lead by wrapping it around the terminal. Now you're ready to solder. To make a good solder connection, first wipe the tip clean and tin it if necessary. Then heat the connection. Place the tip against both the lead and the terminal. Keep it there until the total joint is hot enough to melt the solder. A small amount of solder quickly applied to the tip will help the transfer of heat. Then move the solder to the opposite side of the connection. Remove the solder first, then the iron. Let the connection cool undisturbed. It's good practice to remove the flux residue after soldering because it doesn't look good and may cause leakage paths. This is what a good connection should look like. It's smooth, shiny, and the solder feathers out to a thin edge. The wire outline is visible under the solder. The best way to unsolder a connection is to remove the solder and then disconnect the leads. To remove the solder, you can use a vacuum bulb, solder sucker, desoldering iron, or desoldering wick. If the component you're unsoldering from a PC board has thick or heavy leads, clip it out before unsoldering the connection to avoid excessive heat causing the pad to lift. The clip-out method also works well when you need to remove bad ICs. To test your retention, let's take a short self-scoring quiz. A pencil and paper will be handy during the quiz. Stop the recorder between questions if you need more time. Question 1. The basic purpose of soldering in electronics is to provide a good electrical connection that's also A, high resistance, B, clean, C, strong mechanically, D, smooth and shiny.
Okay, all right. So the basic purpose of soldering in electronics is to provide a good electrical connection that is also high resistance, clean, strong mechanically, smooth and shiny. Which one of those is right or wrong for that matter? Smooth and shiny? Strong mechanically? So I'm sitting here looking at it, and first of all, I want to say you don't want high resistance, right? Or do you? No, you don't want high resistance, because that would mean that there's going to be a voltage drop right at that point, right? Do you want it clean? Well, yeah, certainly you want it clean. Do you want it mechanically strong? Yeah, because if it's weak, you don't want that, right? And smooth and shiny, you definitely want that, right? Yes, that's what I'm thinking too. Yes, exactly, Sonia. So let's see what they answer. That's what I'm kind of going for here. It's been a while since I've watched this.
C is the correct answer.
But C is the correct action, right?
Is to provide a good electrical connection that's also strong mechanically.
But the basic purpose of soldering and electronics is to provide a good electrical connection that is also strong mechanically. Yeah, but you guys see what I'm saying, right? If it's all dirty and stuff, that might actually induce some resistance into the joint, right? Smooth and shiny means that you don't have a cold solder joint. So I'm kind of up in the air on this one, even though they're saying smooth or strong mechanically, because certainly strong mechanically is what it's supposed to be. Let's see what I think there's a couple more.
Always clean your iron's tip. A, after the iron has first been turned on. B, each time you return the iron to its holder. C, each time you pick it up to use. D, when it starts to look dirty.
So always clean your iron's tip after the iron has been turned on. Each time you return it to the holder. Each time you pick it up to use it. When it starts to look dirty. What do you guys think? All right, let's keep going. See what it says.
C is the correct answer. Get into the habit of cleaning your iron's tip each time you pick it up to solder.
Each time you pick it up to solder.
Question 3.
And actually, that is true. It's almost like a habit. Pick it up. You clean it off on the sponge. I like to add a little solder or retin it, clean it off. Because after it's been turned on, you might not use it for 5 or 10 minutes. You could, but the iron's not going to be hot at that point after you turn it on, right? Yeah, well, they want each time you pick it up to use it. Because think of it, you pick it up to use it, you need to make sure that it's ready to go right there. Now, when it starts to look dirty, I would think so too. Yeah, that might be true, but they say each time you pick it up to use it.
Question 3. You should always solder with a tinned tip because A, a tinned tip lasts longer. B, a tinned tip produces better heat transfer. C, a tinned tip helps produce good solder connections. D, all answers are correct.
What about this one? And I guess there's a little bit of a delay, so I'll kind of hang in there. So you should always solder with a tin tip because a tin tip lasts longer? Question mark. A tin tip produces better heat transfer. A tin tip helps produce good solder connections. Or delta. All answers are correct. I was going to say all of the above, but yeah, when a girl has no name, got it right. Where do you weigh in there, MChav? If you're there, if not, that's okay too. Anybody else wish to comment? Just going back, seeing who all was here, and might be lurking, and that's fine too. All right, hold on. Okay, I'm holding. Oh, man, I'm kind of got a spot going on right here. I wonder if I turn this on. Yeah, it makes me look real pale, but the old green screen, right? Oh, I know what I need to do. D, huh? Hold on. There. Let's kill this one. Or C. Let's see what they say. I think it's all answers are correct. Oh, no worries, MChav. It will be reflected in your grade, though. No problem at all. Let's see what they say. Come on.
All answers are correct.
All
You
answers
should
are
always
correct.
solder with a clean, bright, tinned tip because it'll minimize oxide formation, thus increasing the tip life. A tinned tip also gives better heat transfer, which helps you to make good solder connections. Question 4. List the following soldering steps in their proper order. A. Apply the solder. B. Heat the connection. C. Leave the tip on only long enough to thoroughly melt the solder. D. Wipe the tip clean.
Okay, so list the following soldering steps in their proper order. Yes, you did. Yes, you did. You answered it right the first time. Very good. List the following order steps. Mind melding. What's the order? You apply the solder, you heat the connection, you leave the tip on only long enough to thoroughly melt the solder, you wipe the tip clean. What do you guys think? What's the order? I'll give you guys a couple of minutes there. Mayhem voted A, huh? And hello, unique name goes here. All right, so MChav has said Delta, Bravo, Alpha, Charlie. Mayhem has said Alpha. Unique name goes here, says Delta, Alpha, Bravo, Charlie. List steps in order. And when a girl has no name, says Delta, Charlie, Bravo, Alpha. All right, so I'm going to take a stab at this because it's kind of hard in my head sometimes to think about this, right? So I'm going to say D, B, A, and C. D, B, A, C. Gerlag, yes, I know. D, wipe the tip clean. Clean it, right? First thing you do. Heat the connection. Heat the connection. There's DB. Apply the solder. And then leave the tip on long enough to thoroughly melt the solder. Now, it doesn't say anything about taking the solder off, but really you should take the solder off and then take the tip off. or at least from what I remember a few frames back. Let's see what it says.
To solder, you should first wipe the tip clean.
Wipe the tip clean.
Then heat the connection.
Heat the connection.
Next, apply the solder.
Apply the
And
solder.
finally,
And then
leave the tip
there it
on
is.
only long enough to thoroughly melt the solder.
B,
So the correct order is D, B,
A,
and C.
C. So let's see. D, B, A, and C. You know what you got. Anyway, let's go on.
Question 5. A good solder connection looks A. Dull, B. Smooth and shiny, C. Grainy, D. Crumbly or crystalline.
We all got it wrong, MChev says. MChev says B. I just heard MChev say B. Bravo. Unique name goes here, says Bravo. Is it Bravo or Baker? Bravo, right? Ooh, everybody's going after B. When a girl has no name, says B also. What does Mayhem say? Bravo, yes. I don't know. We do have 11 watching though, which is more that's chatting, but that's okay. Welcome everyone. We're almost at the end of the video, and then we'll talk some more about some of the lesson. So everybody, I think, is agreeing on Bravo. Yeah, there she is. Oh, oh, I gotcha. He says B. So everybody thinks that it's smooth and shiny, and you know, guys, you are correct. Boy, it's backed up still. No, you were not wrong. Everyone is correct. I love that. Crumbly and crystalline.
B is the correct answer.
B!
A good connection is smooth and shiny. The solder should feather out to a thin edge. The other three choices, dull, grainy, and crumbly or crystalline, are what a cold solder joint looks like. Question 6. If you...
And Marcel Roberts, welcome. He got it right too. Yes. So if you use an iron with too high wattage or leave the iron on the connection too long, you can
use an iron with too high a wattage or leave the iron on the connection too long. You can A. Melt the insulation on wires, B. Cause printed circuit board pad to lift, C. Cause measling on PC boards, D. All answers are correct.
Okay, so if you use an iron with too high a wattage or leave the iron on the connection too long, Marcel says D, you can melt the insulation on the wires, cause printed circuit board pads to lift, cause measling. It's like solder. It's like solder getting in between the connections. That's something they mentioned. And honestly, I've never really heard it called that. Yeah, but that's what it means. So we've got, yes, yes, it does. So let's see what they say. Yeah, I have to agree with you. I have to agree with you. I've never heard of Measling either. And actually, I've watched this video many a times, but if I remember correctly, the video said that Measling is too much solder in between connections. Yeah, yeah, yeah. I think D. I think D is it, guys. I do. Yeah, yeah. I think D is it because and here's the logic behind it. Okay, it definitely melts the insulations on the wires. If you leave the soldering on too long, it'll heat up the wire, which in turn goes up the wire, and the insulation kind of takes and melts and shrinks back, basically. It definitely causes printed circuit boards pads to lift, no doubt there. Yeah, you're right. You're right. That's what I know it as, but they said something like that. Hello, John. How are you? Yeah. You know, I'm gonna look up Measling, guys, because okay. So that actually is heating it, right? Yeah. The occurrence of discrete white spots on the base laminate material. But is that caused because of too much heat? Treat it with calamine. All right, let's go. I say it's D also. All answers are correct. Come on, come on, come on, come on.
All answers are correct.
Here we go.
Using an iron with too high a wattage,
Yes,
or
too much
leaving
heat.
the iron on the connection too long, can melt the
Hey,
wire
Chris Nealing.
insulation, cause the pad to lift, or measling on PC boards. Soldering is a skill that
I had to stop it. So too much heat definitely is not good. And calamine lotion doesn't help.
requires both knowledge and practice. You now have the knowledge. Practice what you've learned, and you'll soon be making good connections automatically.
Anyway, guys, with that, I want to say live long and prosper. Thank you for stopping by. Like, subscribe, follow, whatever else, and make comments.